This is going to be the last section in chapter 24. This will be chapter 24, section 24.6. We're going to look at determining the position and size of an image formed by a thin lens by using a graphical method, similar to what we saw in 24.3. We're going to draw a few special rays called principal rays that diverge from the point of the object that is not on the optic axis. The intersection of these rays after they pass through the lens determine the position and size of the image. All right, so what are we looking at here essentially? We're looking at rays that are parallel. That shouldn't surprise you because that's what we started out with when it came to the mirrors. This goes through the focal point and eventually through the virtual image. The second one is going to be the ray through the center of the lens and doesn't really deviate, just cuts straight through. And then we're looking at number 3 here, which eventually does go parallel to our optical axis and then eventually cuts through the image. Now that's for a converging lens. For a diverging lens, we're going to look at the same principles here, except this one is going to kick out this way and we can back project it through a focal point. This one again cuts through the middle, keeps going. And the third cuts through here and eventually goes parallel to the optical axis, back projected. We can see the image over here. So for figure 24.36, we see principal ray diagrams for a converging lens for several optical object distances. You can see it here as it scoots up a little bit closer and closer. We're going to compare each numbered ray with the preceding description, and you're going to have several points that are worth noting, such as here, you can still have up to a certain point, you can have rays that will go through the focal point and then eventually come out parallel with the optical axis. But soon you get to the point here where you can't have that happen. And so, as it mentions here with ray 3, it does not pass through the lens. In other words, as you try to draw this, it gets closer and closer to the edge of the lens until finally, this is sort of a bad set of geometry here to try to prove that. But if you get up real close like this, you would draw a ray from here to here, and it's never going to pass through the lens. That's why it gets dropped out. These two are just fine. And what are you noticing here? As this gets closer, this inverted image over here gets a little taller, gets a little taller, gets a little taller, until eventually it gets to the point where it's at infinity and you can't really see it. As you push this thing even further past the focal point, your image starts to appear over here. It becomes virtual and it actually becomes larger than the object that you had before. So finally, over here, if you have an image that's on this side of the lens, but you still have the rays coming through here, you can see where it comes through here, it goes to the focal point. You've got your image there. You got number 2, which kind of cuts straight through the middle of the lens. And then you've got number 3 here, which goes through the focal point. And then you can see some of it that you can see this is refracted, but then you can also see an image, a virtual image beam that comes over this way. So you can see the object over here, which is not inverted, but still taller than what you had before. So you've got several problems there that you can work through. If you do want me to work any of these, please do let me know. I'm trying to keep the file size here to a minimum, but I don't mind working the individual problems upon request.